Welcome to the deep dive. You're here because, like us, you want to really get to grips with complex topics, but, without getting totally bogged down.
Exactly. We sift through dense material and pull out the key nuggets, basically giving you a shortcut to being properly informed.
And today, we're tackling something pretty fascinating. How different, let's call them thought processes, can combine to produce better outcomes. Our mission for this deep dive.
It's to unpack this idea of collaborative reasoning and composition using some really current research.
Okay, so what have we got lined up?
We've got two main sources today. First, there's a study looking at how multiple large language models, LLMs like GPT-4, LLM, Claude, Gemini, how they work together on some seriously tough PhD-level probability questions.
Oh, okay.
And second, we'll dig into a report about something called composable meta-reasoning components. Sounds a bit technical, but it's really about designing AI to be smarter and more adaptable in how it reasons.
Right, so putting those two together should give us a pretty good picture of this collaborative reasoning idea.
That's the plan. Get a real handle on it.
Okay, let's jump into that first one then, the LLM collaboration study. The first thing that jumps out is the problem itself, PhD-level probability. And sometimes no definite right answer. That sounds tricky to evaluate.
It really is. That's sort of the core challenge, isn't it? If even human experts struggle to quickly verify something, how do you know if the AI is accurate? Or even if the question itself is a good one?
So collaboration is the key they explored.
Yeah, exactly. The researchers figured that by getting these different LLMs to, in a way, tackle the same problem, they could get a more reliable signal. It builds on ideas like collective intelligence, the wisdom of crowds and distributed cognition.
Distributed cognition, like spreading the thinking load.
Precisely. Different agents handling different parts or maybe just offering different perspectives. They were also looking at how these AIs actually reached consensus, agreement.
So how did this collaboration actually work in practice? It wasn't like a virtual meeting room, I assume.
No, not quite like that. Your method was pretty clever. They generated 100 really challenging multiple-choice probability questions.
Okay.
For each question, one LLM was the generator. Then the other three models would try to answer it independently.
Independently, right.
And crucially, they rotated these roles. So every model got a shot at generating questions and answering questions generated by the others.
Ah, I see. That way you can compare how different models answer the same question and also see if some models generate clearer questions than others.
You got it. That was the setup.
So what did they find? Were some AIs better team players than others, more consistent?
Well, the data was really interesting there. They measured full agreement. That's when all three answering models chose the exact same option. Claude and Gemini came out on top there, showing full agreement around 73-74% of the time. Llama, though, was way lower, only about 41%.
And Llama also had the most disagreement.
Yeah, Llama had the highest rate where none of the three agreed. It suggests, potentially, that the questions generated by Claude and Gemini were maybe clearer, leading to more consistent interpretations.
Whereas Llama's questions might have been a bit more ambiguous, open to different reads.
That seems like a reasonable interpretation of the results, yeah. More varied interpretations from the other models.
Okay, that makes sense. But what about situations where maybe not everyone agreed, but a couple did? Did they look at majority opinions?
They did, yeah. They looked at majority vote. So when at least 2 out of the 3 answering models picked the same answer.
Right.
But here's a really key finding. They also measured something they called reliability. This was about how often that majority answer matched the answer given by the LLM that actually created the question in the first place.
Ah, okay. So did the majority usually agree with the question setter?
Interestingly, the majority vote percentages were consistently higher than the reliability percentages, meaning the models often agreed with each other, but that group consensus didn't always align with what the original question-generating LLM thought the answer was.
Oh, so they could form a consensus but still be off relative to the generator's intent.
Exactly. It shows that just having agreement isn't the whole story, especially without that external ground truth. You need to consider the source.
So who was most reliable in that sense? Whose consensus answers most often matched their own intended answer when they were the generator?
Claude actually had the highest reliability score, hitting about 88%. GPT-4 was right behind it. Then Gemini and Llama had the lowest reliability, around 67%.
So again, Claude seems quite consistent there, and Llama shows more variability.
That pattern definitely held, and they backed this up with more stats too. Confidence intervals, for example.
Right, you mentioned those. What did they show?
They basically give a range where the true agreement rate likely lies. Claude's range was the tightest, showing high consistency. Llama's was the widest, reflecting that variability we talked about.
And the other tests, chi-square and Fleiss's kappa. Sounds pretty rigorous.
It was. The chi-square test essentially asked if the agreement they saw was just random chance. For everyone except Llama, the answer was basically no. The agreement was statistically significant.
Okay, and the kappa.
Fleiss's kappa gives a score for agreement strength, sort of correcting for chance agreement. Gemini got a substantial agreement score, Claude moderate, and GPT-4 and Llama were rated as fair.
So pulling that all together, the takeaway from this first study is what? Collaboration helps, but models differ.
Pretty much. Having multiple LLMs tackle these complex, maybe ill-defined problems gives you a way to gauge response reliability. It also, crucially, gives you insights into question quality itself. Some models seem to produce clearer prompts, leading to more consistent reasoning from others. It's a form of collaborative quality control, almost.
Okay, that makes a lot of sense. It's like peer review for AI reasoning.
A good analogy, yeah. Now let's connect this to the second source, the one on composable meta-reasoning components.
Right, this one sounds more architectural. Meta-reasoning. Thinking about thinking.
Exactly. It's about building AI systems that don't just reason, but can also monitor, evaluate, and control their own reasoning processes.
So the AI decides how best to approach a problem.
Precisely. And the composable part means building this capability from smaller, reusable, independent modules. Think Lego bricks, but for meta-level thinking strategies.
Okay, Legos for thought processes. I like that. So instead of one giant thinking brain, you have specialized components.
That's the idea. You might have a monitoring component checking for errors, a strategy selector picking the best algorithm for the task at hand, maybe a resource allocator deciding how much computation time to spend.
It sounds a lot like how people think sometimes. We stop, we check our work, we switch tactics if we're stuck.
Absolutely. The report draws heavily on cognitive science ideas like metacognition, or that gut feeling you get, like a feeling of knowing or feeling of error. AI researchers are trying to build similar capabilities.
Why is that so important for AI?
Because real-world problems are messy, and resources aren't infinite. And AI needs to be rational about how it uses its limited time and computation. Meta-reasoning is about making those smart choices, deciding how to think efficiently to achieve a goal.
So what are the main jobs these meta-reasoning components do? You mentioned monitoring.
Right. Monitoring the process, controlling or regulating it, like deciding to switch strategies or try harder, selecting the best strategy, maybe even discovering new ones, and allocating resources like time or processing power.
Okay. And they even try to formalize this, like with value of computation.
Yeah, that's a key concept, trying to quantify whether doing more thinking is actually worth the cost. Is this extra calculation likely to significantly improve the answer, or is it just spinning wheels?
That makes sense. Now, why composable? Why build it out of these little Lego blocks instead of one big system?
Well, composability brings huge advantages, borrowed from software engineering, really. Reusability is one, use the same error checker in different contexts. Scalability, improve one component without rebuilding everything.
Flexibility, too, I guess. You could swap components in and out.
Exactly. Adapt the system's meta-reasoning for different tasks or environments. Plus, it makes the whole thing easier to maintain, test, and understand because you're dealing with smaller, well-defined pieces. It helps manage the sheer complexity of building really adapted AI.
Did the report give examples of this in action?
It did. For LLMs, they mentioned meta-reasoning prompting, or MRP. The LLM first analyzes the problem and then explicitly chooses the best reasoning method, like chain of thought or something else from a list it knows.
So the LLM itself acts as the meta-reasoner there.
Right. And in robotics, a system called HYDRA uses meta-reasoning components to spot when something unexpected happens in the environment and then figure out how to update its internal map of the world.
And another LLM one, multi-chain reasoning.
Yeah, MCR. That's where a meta-reasoner looks at multiple different lines of reasoning generated by the LLM for the same problem, and then synthesizes them to create a single, hopefully more robust, final answer.
Okay, I can definitely see the link now. The first study looked at multiple AIs collaborating externally, and the second one looks at building collaborative internal components for reasoning, about reasoning. How do they tie into this collaborative reasoning in composition theme overall?
It's a really neat connection, actually. You can think of those individual LLMs in the first study, GPT-4, Claude, etc., as being like distinct reasoning components, each with its own strengths and weaknesses, its own way of approaching the problem.
Hmm.
And the process they used, having them answer independently, then analyzing the consensus and reliability, that whole analysis acts like a form of meta-reasoning being performed on the collective output.
Ah, right. Evaluating the different reasoning paths, the answers from each LLM, to arrive at a more trustworthy result.
Precisely. It's collaborative reasoning, where the composition is the set of LLMs involved, and the meta-reasoning is the analysis layer that assesses their combined output.
So the finding that, say, Claude was more consistent, that could tell you something about what makes a good component for this kind of collaborative composition.
Exactly. If you were designing a system using the composable meta-reasoning approach from the second paper, the results from the first study might suggest you'd want components that behave more like Claude or Gemini, demonstrating higher consistency and maybe generating less ambiguity.
And could you use those same statistical methods, chi-square, kappa, from the first study, to evaluate how well the internal components of a single meta-reasoning AI are working together?
Absolutely. Those tools aren't just for comparing separate AIs. They could definitely be applied within a single complex AI to measure the agreement and reliability between its different internal meta-reasoning modules. It gives you a quantitative way to see if your Lego brick architecture is actually leading to better, more coherent thinking.
This really ties it together. So whether it's multiple AIs working together or one AI with these internal modular thinking about thinking parts, the fundamental idea is improving the reasoning quality by examining how different processes or perspectives combine.
That's the core of it. It's about understanding that the interaction, the composition, the reflection on the reasoning process itself, that's key to getting more robust, reliable, and intelligent outcomes. It moves beyond just raw processing power.
So for everyone listening, hopefully this deep dive gives you new perspective. It's not just about how smart one agent is, but how different reasoning elements, whether separate AIs or internal modules, can collaborate and self-correct through this concept of collaborative reasoning and composition.
Right. And that leads us to a final thought maybe for you to chew on. How could you apply this in your own life? Think about your own learning, or when you tackle a complex problem. What different perspectives, what different mental components or strategies could you deliberately bring together? How could you reason about your reasoning to maybe reach a deeper understanding or a better solution? It might be worth exploring ideas like collective intelligence or metacognition in your own context.